Hello physics students, welcome to the last exciting episode of Gravity. But wait for it, it's about weight. Now, what is weight and how does it relate to gravity? Well, weight in physical science, you learnt that weight is the force due to gravity. And we sometimes give it the equation W equals mg, where that's the mass, it's experiencing the gravitational field, which is G, and that's the weight force. And of course this is just a variation of F equals ma, as is this, which is just a variation of F equals ma, but instead of A we've got G as the gravitational field strength, because what's causing the weight? It's gravity, and the effect of gravity on a mass is causing the weight force that you experience, or which has a force proportional to its mass and proportional to the gravitational field strength. Now, so we have this formula, and we have this formula which describes the mutual attraction or gravitational attraction between two masses, and we can combine them in such a way as to make our understanding of weight and relative to gravity. Now, this is the force due to gravity. This is equal to the weight force, so these two are related to each other, of course, and this is the free fall acceleration. Now, just remember that we keep it a little bit simple in physics. We're not talking about rotating masses. If we rotate something, we have to vary the gravitational field strength a little bit. Now, we also mentioned in one of the previous videos about gravitational field strength, where we gave you the formula G equals gm on r squared. Now, we didn't really have time in that video to go through it because it was going to be quite a long video, but you should recognize, and those who are mathematically inclined would recognize, that this equation comes from the combination of this equation and this equation, which is just a variation of F equals ma. And if you bring these two equations together and cancel everything out, you get this equation here. And so weight and gravity are mutually inclusive, because your weight is proportional to the gravitational field strength you experience. Now, your weight can vary though, and it doesn't vary just because of the gravitational field strength. So on the surface of the Earth you experience a certain weight force because the acceleration is 9.81 meters per second, and as you go up in altitude your weight force reduces until effectively you're weightless. Remembering that weightlessness in space just means that you're falling towards the surface of the Earth, but you're falling with a curvature. You still have weight, and you still would experience weight if something got in the way, because you're experiencing a force. It just happens to be centripetal force. Now, an elevator is a common example to show that sometimes your actual weight varies, and you have what is called a applied weight. And we've all been up and down in an elevator. Unfortunately, in Launceston there's not a huge elevator for a huge skyrise, so you don't get this effect as much, but you've probably felt it, and if you've been lucky enough to go to a skyscraper or something, you would feel it even more so. If the elevator is stopped, your weight force is just mass times gravity. Okay, and this is imagining you're sitting on or standing on some scales. And in some cities they make physics students go off and ride elevators and stand on scales and record this. The Maya elevator is just not quite big enough. Now, when the elevator is going up, you're getting an acceleration is equal to g. In this one, your relative acceleration, ignoring the acceleration due to gravity, but your acceleration otherwise is 0, and here you're getting an acceleration that just happens to be equal to g. And so you're being pushed up, you have your weight force plus you have your acceleration due to the lift going up, and so you would feel twice as heavy. And this just happens because we're saying that the acceleration of the lift happens to be 9.81 meters per second. It could actually be anything. And you'd feel heavy, and you've probably experienced that. And when the elevator is falling, you would experience a less applied weight because you're actually going against gravity, and you would actually, if the lift fell fast enough, for example if it fell at minus 9.8 meters per second, you would actually float, because you'd have a period of weightlessness, because your weight force would be cancelled by the acceleration of the lift down, and you would be weightless. Now, lifts don't do that, because people would float around, or if you happen to be in contact with the surface and push yourself off, you would float up and hit the ceiling. So clearly that's not a good thing. But you do feel a degree of lightness. Anyway. Now, you probably have experienced this, if you haven't, in going on a car or a roller coaster, where if you're going into a circle, you feel quite heavy, you're pushed into the seat, and if you're going on the outside of a circle, like over a little hump in the road, or on a ride in a show or something, you feel light, or you feel lifted out of your seat, and that's all because your weight force is varying, and what we call this is your applied weight. And so in each of these cases, this W means your applied weight force. Now, can gravity be beaten? We've talked about gravity, we've talked about massive stars, we've talked about its being a fundamental force, we've talked about it extending all the way through the universe, and there's really not many places where there's no gravity. But can gravity be beaten? What do you think? Well, of course it can. Every time you get out of your chair, you're beating gravity. It doesn't take much to beat gravity, because gravity is, relatively speaking, a weak force. It acts along large distances, but in the grand scheme of things, it's actually quite a weak force. But are there anti-gravity devices? Can gravity be beaten? There's a couple of videos on your OneNote for you to look at, which suggest that maybe it can, or maybe it can't. Now, there's also some videos where science meets art, and just because you study science doesn't mean that you can't look at its applications within art. And one of those applications are in these Foucault or Foucault, not certain, I've forgotten how to pronounce that, Foucault pendulum videos. Basically, this is a big pendulum that's massive weight, and it's got a very long suspension, so it's a very long pendulum, and once you set it rocking, it's a way of proving, or it's a way that the early scientists proved, that the Earth was rotating on its axis, because the pendulum keeps rocking in the same plane in space, and the Earth actually rotates underneath it. And if you have something like sand or water dripping out of it, you can see this pattern. And there's some very good videos of Foucault pendulums on your OneNote. So have a look at those. There's nothing wrong with meshing science and art together. And in some cases, art needs a little bit of science to get real. Alright. And guess what? That's the end. And our next topic will be electric fields. But you'll have to watch some other videos for that. Cheerio.